We are Team 1B, the PDA floaters, and we have completed Challenge 1. Mafic Fairpay have recorded over 60,000 hours of construction worker data and provided 2 datasets based on worker fatigue, monitored over 8-hour shifts with either 1 or 2 breaks. Our challenge was to understand if Mafic technology could be used to further improve productivity on projects by creating the tool that will generate an optimal shift pattern based on project variables that are input by the user. We have covered all user stories by assessing the data from both a staff welfare perspective for the construction workers and on efficiency of cost and schedule, which is vital to the planners and senior leadership. The key guidance principles are based on fatigue increasing the risk of injury, quality issues, and potential cost increases. The current shift schedules don't take into account worker productivity curves and might not be designed with the greatest efficiency in mind. In order to analyse the data provided by Mafic, we have made some key assumptions to generate forecasted productivity rates for additional work shift patterns.
Our starting point was understanding what the cost saving would be based on the different shift pattern productivity data. To do this, we assign a cost value, which we've called a plan value, to all 15-minute interval data points and multiply the assigned cost value by the productivity rate to calculate what we have termed the earned value per 15-minute intervals. We then applied this to all data points within the shift data pattern to calculate the grand total plan value and earned value for all shift patterns. The next step was dividing the earned value by the plan value to generate efficiency rate for each shift pattern. Once the efficiency rate had been calculated, we were then able to calculate how long it would take a shift pattern to complete a task. To generate this duration, we convert the length of a shift pattern into minutes and multiplies those minutes by the efficiency rate, which generated the actual minutes worked per shift. The next step was to generate the total required duration to complete a task, and this was done by dividing the total required minutes for completion by the actual minutes worked per shift. And this then helped us this then generated the number of days needed to complete the task. Finally, we used the number of days required per shift pattern to calculate the overhead cost per person, the wage cost per person, total cost, and the gang total cost for the length of the task. The results of these calculations highlight the optimal shift pattern for the project.
This is our solution logic diagram. On the left-hand side are the user inputs, through the middle the process inputs, and to the right the outputs. This incorporates all of the steps that we believe would need to underpin the code that would need to be written to develop our calculator app.
Following proof of concept in Excel, we rebuilt the analysis in Power BI to feed into our dashboard. We used DAX formulas and functions within Power Query to pivot our dataset to make it workable. Once the data had been cleansed and modelled, we were able to move on to the visualization aspect to truly understand what our data was showing. Firstly, we put our 5 shift patterns onto a fatigue curve to show the variation throughout the working day, which ultimately shows how close 4 of the 5 shift patterns were. However, the remainder of the visuals go into more detail to differentiate between these. The table visual is color-coded from green to red for lowest to highest cost shift patterns, which highlights how the 2 breaks on 12 hours is the most cost-effective shift. However, when considering the construction worker user story, the 2 breaks on a 9-hour shift, despite being slightly more expensive, would provide a better quality of life whilst almost limiting huge losses in cost effectiveness. Whilst if you look at the bottom right bar graph, you can see that the average percentage efficiency line is in fact highest across the 7-hour 1-break shift pattern. However, when including overhead costings, it breaks away from being the optimum shift pattern from a cost perspective. Hence, our analysis has outlined how the 12-hour shift on the 2 breaks is the optimal shift pattern.
In addition to the Power BI dashboard interface, we've developed a simple mobile application concept. This could work equally as well on the desktop device or as a plugin. It would collect all of the information from the user, and we've been advised that it would most likely require some kind of sophisticated Python script in order to calculate and call up the totals and recommendations based on the inputs. Our calculator would seek to provide multiple recommendations based on primary factors. In this example, they are either financially focused, i.e. delivering at lowest cost, or welfare focused, ensuring a better life balance and in principle a happier workforce. The app would allow for users to fine-tune their requirements and improve the quality of the outcomes by feeding in their own subcontractor rates, leading to a richer and more accurate tool over time.
Going forward, we would like to be able to calculate optimum shift patterns based on different locations and types of trade. For example, what is the impact of a rural-based plumbing project versus a city centre plumbing project? We would like to see the impact of shift patterns at different times of day. For example, a 7-hour shift starting later in the day. And we'd like to look at the breakdown of overhead costs between different types of contractors. Also, we think it would be interesting to look at the impact of bonuses on fatigue. Here we've answered the judges' questions. So question 1, how has the solution been tailored for the technical skills of the target audience? So we've created an initial design for a user-friendly app for the input of project variables and an easy to digest Power BI dashboard for senior leaders and planners to inform decisions. Number 2, how visible are the benefits of the solution? So the benefit of having this tool is that the user will be able to input the details they have about a project, and the tool will provide an optimal shift pattern based on these specific variables. Question 3, how will the solution scale for larger volumes kinds of data? As our data set increases, the optimal shift pattern suggestions will become more accurate. We'll be able to introduce more trades over time and offer the tool to a wider range of senior leaders and planners. For example, we could trial how a 3-day week affects shift patterns and analyse results data to further inform the efficiency of the model.